Welcome to the AI Research Roundup. I'm Alex, and today we're looking at a paper trending on X, published on July 7th, 2025, about 3 days ago. This paper shows that large pre-trained robot models can learn complex real-world tasks with as little as 15% of the data needed by traditional single-task models. The paper is titled, A Careful Examination of Large Behavior Models for Multitask Dexterous Manipulation, 2507.05331v1. And as we'll see, this has huge implications for making robots more capable in general. The authors rigorously test these large behavior models, showing they not only learn faster, but are also more robust to unexpected changes. Alright, so this first figure gives a great overview of their whole process. It starts with pre-training their large behavior models, which are robot AI models, on a huge dataset from different real and simulated robots. Then these models are fine-tuned, getting specialized training for a specific new job. The charts on the right really show the payoff. The red line, their fine-tuned model, achieves much higher success than a standard model, using just a fraction of the data. This is even true under distribution shifts, which means changing objects or lighting to test robustness. Building on that idea of robustness, these charts really break down the performance. We're looking at violin plots here, which are a way to visualize the range of likely success rates for many different tasks. The top charts show performance in normal conditions. You can see the red plots, representing the fine-tuned large behavior models, are consistently better than the gray single-task models. But the real story is in the bottom charts, under a distribution shift, where things like objects or lighting are changed. Here, that performance gap widens, showing the fine-tuned models are far more robust. So, building on that, these next charts look at performance on completely unseen tasks, jobs the models weren't pre-trained on at all. In both hardware and simulation, the red fine-tuned models consistently outperform the gray single-task models. The bottom row even looks at task completion, a measure of how much of the job the robot got done. And the story is the same. The line charts on the right then show the scaling laws, illustrating how performance improves with data. This really highlights that the fine-tuned models achieve high performance with far less task-specific data. Drilling down into those simulation results. These charts show us what happens on unseen tasks when there's also a distribution shift. The violin plots on the left, which again, show the range of results, make the difference really clear. The red fine-tuned models consistently outperform the gray single-task models, both in full success rate and in task completion. The little A and B letters you see are from a statistical test, basically confirming that the A results are genuinely better. This shows the pre-training provides a powerful and robust foundation for learning. Okay, so to understand how these models achieve such robust performance, this diagram shows their core architecture. On the left, we see the inputs, what the robot sees via its cameras, the language command, like cut the apple, and also proprioception, which is the robot's awareness of its own body's position. These inputs feed into the central large behavior model Diffusion Transformer. This is a powerful type of model that generates a plan by starting with random noise and refining it into a sequence of concrete actions, which you see on the right. And to train that complex architecture, this table details the specific hyperparameters, which are the settings that control the learning process. You can see the initial pre-training uses a very large global batch size. That's how many examples it sees at once, and a higher learning rate to learn general skills. But the key takeaway is in the steps row. The fine-tuned models need far fewer training steps, for example, 30,000 for real tasks, compared to the 100,000 steps for the single-task models. This really quantifies that data efficiency benefit we've been talking about. So to wrap things up, the main takeaway is that large behavior models, which are these big pre-trained models for robot control, are incredibly effective. When you take one of these models and then fine-tune it, meaning you give it a little extra training on a specific job, it becomes far more data efficient and robust than a model trained from scratch. This is especially true when conditions change. The research makes a strong case for this pre-training and fine-tuning approach to build more capable generalist robots. And that's our roundup for today. Thanks for tuning in. I'm your host, Alex.